Welcome to this explainer. I'm really glad you could join me today. Let's take a collective breath and step away from those heavy, stressful textbook lectures for a bit, all right? Today, we're going to go on a super relaxed, kind of fascinating exploration of a technology that is quietly shaping our entire future. We're talking about the elegant, totally silent power of solar cells.
So here's a genuine question for you. Have you ever just stopped and looked up at those dark, quiet panels resting on a rooftop? Really thought about them? There are no gears turning up there, no engines roaring, no smoke billowing into the sky. It's just a flat surface, basically just basking in the sun. Yet somehow, that completely silent, motionless pane of glass and silicon is generating the electricity we need to power our laptops, our lights, our whole lives. How does that everyday magic actually happen?
Well, that brings us right to the core scientific concept we're exploring today, the photovoltaic effect. It's simply the process of converting light energy directly into electrical energy. And honestly, what I absolutely love about this definition is the word directly. Think about it. In most power plants, we're burning fuel to boil water, to make steam, to spin this massive turbine. It's loud, and it's incredibly complex. But here, the transfer of energy happens directly at the chemical level with literally zero moving parts.
Section 1. Anatomy of a solar cell. Zooming into the microscopic sandwich.
To really understand this magic, we kind of have to zoom in on the structure. A solar cell is essentially a carefully constructed microscopic sandwich. Right at the very top, we have an anti-reflective coating. Its entire job is incredibly welcoming. It simply reduces the reflection of sunlight, making sure that as much light as possible actually enters the cell, instead of just bouncing right off. Below that, we find the meat of our sandwich, two distinct layers of a semiconductor material, which is usually silicon, and then finally, at the very bottom, there's a metal back contact layer just waiting to collect the generated power.
Now, the absolutely crucial point here is understanding those two middle layers of silicon, because they are definitely not identical. On one side, we've got N-type silicon. The N stands for negative. This silicon is doped, which just means intentionally mixed with elements like phosphorus. That gives it this massive abundance of extra electrons. Imagine a totally packed, crowded room of energetic people. Then, on the other side, we have P-type silicon. The P stands for positive. This layer is doped with elements like boron, which actually leaves it with fewer electrons. It creates what chemists call positive holes. So if the N-type is that super crowded room, the P-type is a room full of empty chairs just waiting to be filled.
Section 2. How light becomes electricity. The journey of a single photon. Okay, so let's bring the sun into the mix. First, sunlight hits that welcoming anti-reflective coating. These tiny packets of light energy, called photons, enter our silicone sandwich and get absorbed. This absorption provides a burst of energy. It's like a spark. It excites the electrons in the silicon, giving them the energy to basically jump up out of their seats, creating what we call electron-hole pairs. So now we've got moving electrons. But to get usable power, we need them all to flow in one specific direction.
And that brings us to, honestly, the most beautiful part of the whole design, the PN junction. This is the invisible boundary right between the N-type and P-type silicon. Right at this boundary, a natural electric field forms. When the sunlight excites those electrons, this electric field acts like a one-way turnstile. It forcefully separates the charges, pushing the negatively charged electrons toward the top layer and the positive holes toward the bottom. With nowhere else to go, the electrons are forced to travel out of the cell through those metal contacts we mentioned earlier, traveling through an external circuit before finally returning to the bottom layer. And that flow of electrons, that is your electric current.
Section 3. Solar power in real life. Zooming back out to the world around us.
Because solar cells can be scaled from a single tiny square to massive, sprawling fields, they are incredibly versatile. We use them for residential and commercial power, placing them on rooftops to silently run our homes. They're in portable chargers, keeping our phones alive when we're miles off the grid. Fun fact, the very first practical use of solar cells was to power the Vanguard 1 satellite way back in 1958. And today, they are still the primary power source for satellites and space stations, operating flawlessly in the total silence of space. Speaking of off the grid, down here on Earth, they are an absolute game changer for remote and rural electrification, bringing reliable light and power to villages far away from traditional power lines. And right in your own neighborhood, they're quietly running our streetlights and traffic signals, making our cities so much more sustainable.
To wrap up our journey today, I want to leave you with a super low-pressure summary. You really don't need to memorize every single chemical interaction we talked about, but if you take away just one thing, let it be this core truth from our source material. Solar cells convert light energy directly into electrical energy using the photovoltaic effect. That's the whole shebang. It is simply nature, sunlight, and human science, silicon engineering, working together in perfect, quiet harmony to generate the power we need.
Thank you so much for exploring this with me today. It's my hope that this explainer has made the whole topic feel a bit more accessible and clear. The next time you step outside and feel the warmth of the sun on your face, take a quick moment to look at a solar panel, if you see one, and just think about that invisible, microscopic dance happening right above us. With solar technology becoming thinner, cheaper, and more flexible every single day, what happens to our world when literally every surface around us becomes a silent generator? Stay curious, keep learning, and I'll catch you in the next explainer.